Hello everyone, in this video we are going to discuss yet another type of force, tension and compression, which are basically elastic forces. We're also going to introduce a new law known as the Hooke's law. So Hooke's law basically provides us with a formula to actually explain tension and compression mathematically. So for learning objective, we have finally moved on from objective C. So we are now at objective A, record and apply Hooke's law to new situations or to solve related problems, meaning to say that you need to define Hooke's law, you also need to apply Hooke's law in calculation to solve problems. So for tension and compression, what exactly is tension? Basically, tension is a pulling force exerted by string, cable, rope, okay, on another object. So basically anything that is taut, okay, a taut rope attached to a load is under tension. So tension, do take note that it is actually a pulling force. Okay, so tension pulls on the rope, and as a result, the rope pulls back on the load. So this is actually Newton's third law. So do take note, okay, the key word here is pulling because that helps to explain the direction of the tension. So essentially, tension is always directed away from the body and along the rope at the point of attachment. So let us look at some diagram to actually explain this in detail. So you see that I have a load that is hanging on the ceiling via a rope. So if I were to break down the free body diagram of the ceiling and the rope itself, you can see that the tension is acting away from the ceiling because it's a pulling force, it's away from the ceiling along the rope. So same thing for the load, okay. The tension is also acting away from the load, okay, along the string. So for the two tension, okay, acting on the ceiling as well as the load, they are basically having the same magnitude because they are actually action-reaction pair. Okay, so another example, figure 2. So we have a connected bodies whereby load A is actually placed on the table, whereby load B is actually free hanging. So they are connected along a string as well. So if you were to draw individual free body diagram, you can see that the tension is always away from A and B along the string itself. So this is how tension is always acting on, away from the body, along the rope. So moving on to compression. So basically compression is a compressing, or in the opposite way to tension is a pushing force that acts on the object. So if let's say I place a heavy load on the column, okay, so the load will be pushing onto the column, and the column in reaction will be pushing, okay, a compressive force on the load itself. So the load pushes on the column, and by Newton's third law, the column also pushes back on the load and the ground simultaneously. So do take note in this case, therefore, the direction of the compression force is always towards the body, because when we push something, we are acting a force towards the object. Okay, so it is always towards the body along the column. So in this case, I have a heavy load placed on top of a column and the ground. So if we were to split it into three individual bodies, so on the load itself, you have a compressive force acting on the load, acting towards the load. On the column, you can see that the load will therefore also in reaction exert a compressive force on the column, and the ground will also exert a compressive force towards the column. So finally on the ground, you can see that by action-reaction pair, by Newton's law, the column will also exert a compressive force towards the towards the ground itself. So just understand compression always pushes onto the body. So the magnitude of the compression is also the same for different bodies because they are essentially just different pairs of action-reaction pair. So moving on to Hooke's law. Hooke's law states that if the limit of proportionality is not exceeded, the extension is directly proportional to the load or force applied. So something that I want you to take note here, there is a condition attached before Hooke's law is even applicable. And the condition here is that the limit of proportionality is not exceeded. You may not fully comprehend or appreciate what the limit of proportionality really means, but that's alright. I'll be explaining that later in the video. But what I want you to take note here is in your definition of Hooke's law, you need to describe this condition that the limit of proportionality must not be exceeded. Only then the extension is directly proportional to the force applied. This context is pretty similar to how principle of conservation of momentum is also defined. For PCOM to be even applicable, the net force acting on the system must be zero. So in the context of Hooke's law, for Hooke's law to even apply, the limit of proportionality is not exceeded. So do take note, all these things you need to include in your definition. So from the definition itself, you can also understand that, okay, mathematically what it means is that force is equal to kx, So force proportional to extension. So the notation F represent the force applied to the material. X represent the extension or compression of the material. K is what we know as the constant of proportionality, or in some other words, force constant. But what it is more commonly expressed among the teachers as well as A level is actually this thing called spring constant. So whenever you read a question, if it's defined as constant of proportionality or force constant or spring constant, you must know that what they are referring to in this case is K. And the unit for K is basically Newton per meter. So common mistake. So do take note that F is equals to Kx. What X represent is not the natural length of the final length. What X represent is actually the change in length of the material. It is the difference in length. It is the extension or compression, okay, not the final length. So basically X is basically equals to the final length minus the natural or unstretched length of the spring or rope or string, whatever it is, okay. So in this diagram, we have shown you what X really represent. It represents the extension. So it is the difference between the final length and the natural unstretched length.
Well, so like just how with great power comes great responsibility, with a new equation, you have a new graph to learn. Yeah, lame jokes. But anyway, for force plotted against extension, this is how the graph is going to look like. So it should be obvious that since F equals to Kx, there must be a straight line portion that passes through the origin. So this will be the straight line portion that passes through the origin that actually obeys Hooke's law. So anything between O and P, we say that the force is directly proportional to the extension. But you can see that beyond point P, okay, the graph is no longer straight line. There is actually a curve over there. So what we refer P to is sometimes known as the limit of proportionality. So beyond that point, the force is no longer proportional to extension. And Cambridge sometimes refers to this point as the elastic limit. So technically, there's a difference between proportionality limit and elastic limit, and I'll be discussing this later. But Cambridge, or for A-level purposes, they will sometimes just combine these two as a single point. And finally, the gradient of the straight line graph is actually the spring constant, so that should be obvious from the equation as well. So the larger the value, the more stiff the spring is. So you can actually see this by thinking along the line that if I were to draw a steeper line, you can see that for the same extension, I actually require a greater force. So therefore, we can conclude therefore the larger the spring constant, the greater the stiffness of the spring. So to discuss a little bit about how work done is related to Fx graph. So in O level, you have learned that work done is actually equals to force times distance. So this is nothing wrong, but for the purpose of A level, you must also understand that this is only true if the force is constant. So if the force is actually a variable force, how we actually calculate work done is supposedly the integration of f dx, or in other words, it is basically the area under fx graph. So it will do good for you to differentiate this against FT graph, okay, something that you have learned in dynamics, because at the end of the day, for H2 physics, you'll be learning many types of graph, and it actually pays and both do you well that if you actually takes time to sometimes differentiate the graph, consolidate them, and understand, okay, in the right way. So for area under FT graph, that is actually impulse, or in other words, the change in momentum. For area under FX graph, okay, it is basically work done, or you can also refer it to energy because work done and energy are basically the same type of quantity. So basically this graph, the shaded area, the gray area is basically the work done to actually stretch the spring, or it is also known as the elastic potential energy. So to word it as how your lecture notes actually words it. So when a wire is stretched without exceeding its proportionality limit, the energy used to stretch the wire is stored as the elastic potential energy in the wire. So this elastic potential energy, which is also sometimes known as the strain energy. Okay, strain energy is also a type of terms that will be used in A-level questions. So this elastic potential energy or strain energy may be represented by basically the area under fx graph, something that we have just discussed in the previous slide. So elastic potential energy equals to work done on the spring. It is basically just area under fx graph. Okay, so for a material that obeys Hooke's law, basically the straight line portion between O and P, so the EPE is basically the shaded area, which is basically the area of the triangle. So half base multiplied by height. So half fx. And since we also know that f is equal to kx, we can substitute this into f, thereby giving us half kx squared. So both formula is useful. You will need to actually remember them. So moving on to describe what is the difference between the proportionality limit as well as the elastic limit. So basically, anything that is stretched within the elastic limit, we will say that the spring is showing elastic behavior, meaning to say that even beyond the proportionality limit, okay, the spring, as long as it's stretched before the elastic limit, will go back to the original length when we remove the force. So even beyond the proportionality limit, but before the elastic limit, okay, the spring will still return to its original length. But what is important, okay, is that beyond the elastic limit, okay, the spring will suffer a permanent deformation when the force is removed. So meaning to say that the material does not return to its original length, there will be a permanent extension, there will be a permanent deformation. This point, beyond the elastic limit, suffering a permanent deformation is much more important to actually understanding the differences between elastic and proportionality limit. Because for the purpose of A-level, these 2 points, like I mentioned just now, they will normally will not be differentiated and will just be applied as if they are the same point. So understanding how work does applies in this case as well. So if let's say I stretch, okay, a spring or a wire to point X, then the energy, okay, the work done to stretch the spring is basically under the area under the graph, and that green area that we see there is basically the EPE. And that energy is 100% recoverable because once I remove the load or the force, there will be no permanent deformation. The spring will return to its original and stretch length, and all these EPE will be recoverable. But if let's say I actually stretch the spring beyond the elastic limit to point Y, so what happens here is the total work done required to stretch the spring to point Y is actually both the area yellow color as well as the green color. But what is stored as the EPE is only the green color region. And that region will be recoverable when I actually remove the force. But the yellow color is basically the work done to permanently deform the spring, and it will not be recoverable anymore because of the permanent extension. And how is all this going to be used for A-level can be seen from this extra example that I've included here from H1 2010. So here we have a metal wire that has been stretched by a varying force F, causing the extension to reach Q. And then when the force is reduced, okay, the relationship become QR, so there's a deformation between O and R. And the question asks about the elastic potential energy stored in the wire at point Q. So based on what we have discussed in the previous slides, we should know that the answer therefore should be Z. So moving on to our lecture note example 6. Here we have a wire stretched elastically by a force of 200 Newton, causing an extension of 4 mm. Then the force is increased to 250 Newton. The wire still behaves elastically. So how much extra work that is done in producing the additional extension? So here you can see that the question mentioned about elastically. And from what we have mentioned just now, we do know that Cambridge actually mix up elastic limit with proportionality limit together. So here we can therefore assume Hooke's law will still apply. So knowing that, we draw a fx graph. So basically the extra work done to produce the additional extension is basically the yellow highlighted area. So in order to find the area, therefore we will need to find the new extension. To find the new extension, maybe we will need to use Hooke's law, F equals to kx, knowing that at first force is 200 Newton, and then we have an extension of 4 mm. Therefore, we can actually find the spring constant K, okay, 50,000 Newton per meter. So the new extension when the force is 250 Newton is equals to 250 divided by 50,000. Essentially, this is using the formula X is equals to F over K. So we can find the new extension, which is actually 5 mm. So we can actually find the area, the yellow highlighted area using the area of trapezium. Or otherwise, we can use basically the final EPE minus the initial EPE, which is basically the bigger area minus the smaller area. So that will give us the yellow color. So basically press your calculator, we can therefore get, okay, the final answer as 0.225. So here what I have used for EPE is using the equation EPE is equals to half Fx. Okay, so you can also use half kx squared since we have already found k, so both way will work. So moving on to work example 7, here we have a scale of a spring balance that reads from 0 to 100 Newton, spans a length of 0.15. So we are required to find the strain energy, okay, when the balance shows a reading of 14 Newton. So basically same thing, we will still be using F equals to kx, okay, and to find the spring constant k using F naught over x naught, basically 100 Newton divided by 0.15. So we get k equals to 666.7. So to find the strain energy at 40 Newton, we need to find the extension at 40 Newton, which basically we can find also by using F over K. Since we know F is 40 Newton and then we divide by the spring constant K, we can find that the extension at 40 Newton is actually 0.06 meter. So now to find the strain energy, we can use EP equals to half kx squared. Okay, so we find that it is actually 1.2 joules. So at the same time, if you wish, you can also try to find EPE equals to half Fx. So half times F as 40 Newton multiplied by the extension 0.06. You should also get exactly 1.2 joules. So moving on to part B, here we need to find the increase in strain energy when the reading increases from 40 Newton to 80 Newton, very similar to example 6. So here, increase in EP basically is the difference of the EP when the reading is 80 Newton and when it is at 40 Newton. So basically just half kx squared minus half kx squared. So how do I actually find the extension at 80 Newton? So basically we are making use of the directly proportional relationship between the 100 Newton and 0.15. So since 100 Newton is at 0.15, at 80 Newton, it will therefore be 80 over 100 times 0.15. So in the same way, to find the extension at 40 Newton, all I need to do is take the 40 Newton divided by 100 multiplied by 0.15. Although I can also substitute the extension found in part A into here. So basically, pressing the calculator, I can get 3.6 joules. So finally, one last thing that I want to mention here is in this question, we are basically using the term strain energy. Okay, so you need to understand that strain energy basically refers to the same thing as elastic potential energy as mentioned in the earlier slides. So finally, I would just like to point out one very common mathematical error students make. So students always calculate the change in EP equals to half k bracket x1 minus x2 squared. So basically, half k delta x squared. Okay, but this is the wrong way to calculate the change in EP. How you should calculate the change in EP is basically just taking final EP minus initial EPE. So basically half k x1 squared minus half k x2 squared, not half k delta x squared. Okay, if you look at this equation here, basically half k x1 squared minus half k x2 squared, if you want to factorize, you can only factorize half k out. X1 squared minus x2 squared is staying within the bracket. Okay, it is not half k x1 minus x2 holding square. The square doesn't come out of the bracket. Okay, so this is wrong. This is correct. So the best way to remember to calculate change in EPE is really just taking the final EPE minus the initial EPE. So finally, we are at the end of this lecture. In the next lecture video, we are going to discuss about the last type of force, upthrust. And for upthrust, it will be the most difficult type of forces that we have discussed so far and is also the most heavy in content. Also, at the same time, I also like to highlight that there are some further examples housed under appendix, page 26 and 27 of your lecture notes. These examples discuss about springs connected in series as well as in parallel. So even though these examples are under appendix, I think it is really useful for you to read them to have a fuller understanding of tension and compression. So do read them, and if you have any problem, then let your tutors know and then have a discussion with your tutors. Okay, thanks, bye.